So, in a course on the topic of extraterrestrial life, we are first going to address the question, what do we expect that extraterrestrial life to be like? Now, this isn't so much a question of what do we think it will look like or how aliens might think. We're really asking the question, what chemistry, what atoms and molecules will that life most likely be based on? Now, we notice that all life on Earth is based on carbon, and all life on Earth requires water as a necessary part of its chemistry. In order to be alive, everything on Earth has water and carbon. And I want to argue that it is reasonable to expect most life in the universe is probably going to be based on carbon, and most life in the universe will probably have water as an essential component. Now, I'm not going to say all life in the universe will always be based on carbon and water, but I think it is reasonable to expect that the majority of life elsewhere in the universe will probably be carbon based and have water as an essential component. So, we said life possesses some degree of complexity. Now, what do we mean by this? Well, we have really complex atoms and really complex molecules and really complex chemical processes for life. So why can't life really be based on hydrogen and fluorine? There's hydrogen in the upper left, here's fluorine right down here. Well, hydrogen and fluorine can only bond to one other molecule, oxygen and calcium. Well, we need calcium for healthy bones. So calcium is involved in life, and oxygen is what we breathe. Oxygen and calcium can only bond to two molecules. Now, let's imagine that we wanted to make a really complicated molecule, something like what's shown here on the left. What types of atoms would be able to build up a complicated molecule like this? So, what types of atoms would form the backbone of a really funky structure for a molecule? In the case of hydrogen and fluorine, for lack of a better word, I'm going to say that an atom that can only bond to one other molecule will have to always be on the outside of that molecule. Now, don't take the phrase outside too directly. I just mean that if I have this blue atom and this blue atom is bonded to this red atom, this blue atom cannot bond to anything else. So this red atom could bond to several atoms, but the blue atoms in the picture, which I just zoomed in from right over here, these cannot bond to anything else. So these kind of are a way to cap the end of a molecule, so to speak. So an atom that is only able to bond to one other part atom in a molecule, that atom can't really form the backbone or the structure of that molecule because it can't bond to too much. Well, what type of molecular structures can we build with atoms that can only be bound to two atoms? Well, if an atom can only bond to two other atoms, there are three possible arrangements. You could form a double bond with something, so you could have both your bonds to another atom. So this yellow atom in the middle is able to bond has 4 bonds at its disposal. The red atoms shown on either side have 2 bonds at their disposal. So you have a double bond here and a double bond here. So the red atom could form a double bond on the outside of a molecule, much like in the previous slide. Or you could have, if you're only allowed 2 bonds, you could form a really long chain, or you could form a closed loop of some form. Now, in all of these cases, the manner in which you're able to bond is limited. If you just have a closed loop, well, then you're not really going to be doing too much. And if you have a long chain, well, you could continue the chain, but you can't have the chain branch off, or you can't have any fork in the road or junction between different chains of molecules. So the intricacy of your molecule, if you're only able to bond to 2 other molecules, is somewhat limited. You can't really form some really unique patterns like this that could lead to the really complex chemistry that's necessary for the processes of life. So, life involves a lot of complex chemistry, and in order to create really complex molecules like proteins and DNA, we need some type of atom that could bond to many other atoms. And carbon is a wonderful example of an atom that could fit this bill. So, carbon can bond to up to four other molecules. So, this allows carbon to form the basis of some really complex molecules like some amino acids, proteins, DNA. So this is one of the reasons why we say carbon, all life should probably be based on carbon. Carbon allows you to build these really complicated molecules that allow you to have your really complicated chemistry. Because if you're going to form some type of molecules that form into cells that are dividing, at the fundamental level, the cells that divide, the cells that form animals and plants that reproduce, you're going to have a lot of interesting chemistry going on. So you need some really interesting molecules to make these life processes go. Now, in addition to allowing the existence of a really complicated molecular structure, carbon bonds strongly to other atoms, and this is going to be pretty important. So, before I talk about this some more, a chemical reaction is a process where one or more molecules will do something with one or more other molecules, and then at the end of the day, they combine or break apart in some manner. Now, there are different types of chemical reactions. You could have an atom or molecules combine to form something bigger. You could have atoms and molecules that are combined break apart. You could have an atom or some molecules that are combined, and then something else could come kick one part away. In a double displacement reaction, they could swap pieces with each other. So there are a whole bunch of different types of chemical reactions, but a chemical reaction is basically you take one or more molecules, you combine them or break them apart and form new molecules together out of their component parts. Now, if you're going to have chemical reactions, these bonds cannot be too strong, but they also can't be too weak. So if the bonds holding the atoms together are really, really weak, then these bonds are going to break apart really easily. And if we want living things to have complicated molecules, you can't have it where these molecules break apart super easily, because then these living things will not have whatever molecules they need to be able to be alive. So these molecules need to be stable, but at the same time, these molecules can't be bound so tightly together that you never could break these bonds apart. Because if you're not able to do chemistry, if you're never able to actually break these bonds and form new chemicals and molecules, then that means there's no chemistry and none of these life processes that are able to go on. So the molecules that are broken apart really easily, well, they'll just react right away before they could have a chance to get to a level of complexity like proteins and DNA. And in that case, you're never going to achieve the level of complexity that you need to have self-reproducing molecules and molecules that could interact with their environment and things like that. So carbon does tend to bond very strongly with other molecules, but carbon doesn't bond so strongly that it's impossible to have these bonds broken. So this is another reason why carbon is really nice for life. Carbon has 4 bonds. It could bond up to 4 other atoms, so you can make your complicated structures. And carbon bonds strongly, but not too strongly. Silicon, as an example, is another element that could bond to 4 other atoms. So there's silicon right below carbon on the periodic table. And so you might ask the question, why can't life be based on silicon instead of carbon? Well, one of the issues with silicon is when silicon bonds with other silicon atoms, these bonds tend to be really weak. And we don't want molecules to be broken apart too easily. So this is one thing silicon doesn't have going for it. When silicon bonds to oxygen, that substance is very unlikely to react. It's going to be very inert. And if you want to have a substance that is necessary for life, that substance should have the capability of reacting. You don't want it to react super easily, but you do want it to do something because you need chemistry and chemical reactions to occur if you're going to have life. So this property of being inert is not really ideal if you need life to continuously have different chemical reactions occurring. If you bond silicone with two oxygen atoms, you basically form rock or sand, quartz crystal. These are all varieties of silicon dioxide. And these have really, really strong bonds. And if the bonds are too strong, then again, you're never going to have chemistry. Now, there are other atoms that have 3 or 4 bonds to them: boron, nitrogen, phosphorus. And I'm not going to go through all of these, but a lot of these other atoms have similar issues like silicon does. So this is one of the reasons why we think carbon is probably going to be the basis of most life in the universe. And again, it's not to say that carbon will be the basis of all life in the universe, but if carbon is the basis of 99.99% of all life in the universe, then it is reasonable, if we are looking for life elsewhere in the universe, if we are looking to discover the first example of life elsewhere in the universe, we probably want to be looking for something that's based on carbon. Now, it's also reasonable to expect that if or when we find life elsewhere in the universe, that life will probably be based on common substances in the universe. The first instance of we finding life elsewhere in the universe, it probably won't be based on some really exotic rare atoms that are in a very small supply compared to more common atoms. So like carbon, germanium is an atom that can bond to 4 other atoms. You probably won't have life living deep under the Earth's crust. There might be some carbon-based life near the top of the mantle. When I was writing these slides, I was going to say there's no life inside the mantle, but then a quick Google search, I found some popular science articles that seem to suggest life might exist in the very upper layers of the mantle. I find that surprising, but that would be really interesting if it's the case, and so I'm not going to go into that more. But you probably won't have life way deep down near the core of the Earth in the lower mantle. So if life is going to come to evolve and grow on a planet, it will probably be made of a lot of stuff that is on that planet. And if we look at the composition of Earth's crust, the Earth's crust is mostly oxygen and silicone. Well, we argued that oxygen is not a good backbone or basis for life because oxygen only bonds to 2 other atoms, so you can't make those complicated molecules. We argue that silicon is probably not going to be a good basis for life, even though silicone could bond to 4 molecules and build complicated structures. Silicon still has the issues of it'll bond too strongly or not strongly enough, and so you won't have interesting chemistry. Then you have your aluminum, iron, calcium, other stuff. You don't see, notice on this plot, you don't see carbon and you don't see germanium on this plot for the common substances in the Earth's crust. Well, I say when I talk about probably, I do want to acknowledge that human creativity is limited. Life is complicated, and I'm not a chemist, but I think it's reasonable that complex molecules will be destroyed in really hot environments because those environments are so energetic going around with the atoms bouncing off each other. If you make a really long, complicated molecule, like that protein molecule I had for many slides back, that protein molecule will probably be destroyed in the temperatures deep inside the Earth. So in my opinion, it's reasonable that you will almost never find life deep inside a planet. But again, I acknowledge my creativity is limited. Maybe there's a way to make that happen, but you will need to get around the barrier of we need complicated chemistry deep inside a substance where the conditions may not be favorable for the existence of complicated molecules. But again, of course, it's possible I'm going to be wrong on some of these. So why are we giving no love to germanium? Carbon is thousands of times more common in the Earth's crust than germanium. So I don't know much about the properties of if germanium would have the same problems with not strong enough or too strong of bonds like silicon, but If carbon is more common than germanium and carbon allows for those four bonds that we want, so then carbon is probably going to be the basis for life on Earth. Another thing that germanium has against it is germanium doesn't really dissolve nicely in water. And this brings us to another important ingredient we believe for life, and that is water.